স্যার সায়ান্নদীপ ব্যানার্জি।
সায়নদীপ ব্যানার্জি, ওকে। সায়নদীপ, আচ্ছা, এইচও আছে একটা, হ্যাঁ।
হ্যাঁ স্যার।
আচ্ছা, এবার অন্যরা। অরিজিৎ চক্রবর্তী, ঠিক আছে। তারপর প্লিজ, হ্যাঁ, তাড়াতাড়ি ক্লাস শুরু করতে হবে।
গৌরাঙ্গ দাস।
গৌরাঙ্গ দাস পেয়ে গেলাম। তারপরে শুভ,
অর্ণব বড়ুয়া।
সৌভিক চ্যাটার্জি।
আচ্ছা, সৌভিক চ্যাটার্জি,
স্যার সৌভিক চ্যাটার্জি।
আচ্ছা। তারপর
স্যার দীপ কুমার মন্ডল। আমি স্যার কুমার
কুমার
স্পেলিংটা স্যার চ্যাট বক্সে লিখে দিয়েছি।
ঠিক আছে,
CWMAR।
ঠিক আছে, এখানে দেখলাম দীপ মন্ডল হিসেবে আছে এতে। ঠিক আছে।
অর্কপ্রভু দাস।
অর্কপ্রভু দাস, তোমার একটা এইচ আছে না?
হ্যাঁ স্যার।
ESH, হ্যাঁ, ঠিক আছে।
অর্ক মাইকা।
অর্ক মাইকা।
স্যার শাহানা রায়।
শাহানা রায়, ঠিক আছে।
স্যার তুহিন দাস।
তুহিন দাস, ঠিক আছে।
স্যার শাশ্বত দাস।
আরেকবার বলো, কি নাম বললে? শাশ্বত দাস, হ্যাঁ, পেয়েছি।
শাশ্বত।
তারপর
স্যার আমারটা লিখলাম।
হ্যাঁ, বলো।
অর্ণব বড়ুয়া।
কি নাম? অর্ণব বড়ুয়া, না লিখিনি, লিখছি। অর্ণব বড়ুয়া। দাঁড়া, অর্ণব বড়ুয়াকে আমি ক্লাসে দেখতে পাচ্ছি কি? তুমি অর্ণব বড়ুয়া কি হিসেবে ঢুকেছো গো ক্লাসে?
স্যার আমার ইমেলেই ঢুকেছি, অর্ণব বড়ুয়া 71 বলে আছে।
ক্লাসে দেখতে পাচ্ছি না।
না, আমি গুগল লিংকে পেয়েছি, মানে অ্যাজ ক্লাসরুম পেয়েছি।
ক্লাসরুমে? দাঁড়াও, দেখছি। ও আচ্ছা, এক সেকেন্ড। তুমি পরে এসছো না? হ্যাঁ, ঠিক আছে।
স্যার একজন জয়েন করতে চাইছে।
আচ্ছা, আলমগীর সাপুই, হ্যাঁ, আলমগীর সাপুই হয়ে গেল। হ্যাঁ, পেয়ে গেছি। অর্ণব বড়ুয়া। আর কেউ আছে?
স্যার আরো একজন আছে মনে হয়, মাইকে প্রবলেম, অর্চনা কুমারী।
অর্চনা কুমারী, আমি নাম দেখতে পাচ্ছি। একজনের ক্লাসরুমে দেখতে পাচ্ছি, তার নামটা বুঝতে পারছি না। ANINASS।
হ্যাঁ স্যার, ওর নাম হচ্ছে অনির্বাণ নস্কর।
অনির্বাণ নস্কর, সে আজকে নেই এখানে ক্লাসে?
না।
আচ্ছা আচ্ছা আচ্ছা, অনির্বাণ নস্কর, ঠিক আছে, ওকে, so that's good enough. So the first question that I have is very clear. Is there anybody in the class who is completely unable to speak or understand the Bengali language? If there is a single person, I will speak only in English.
Yes, sir.
Good. So we will conduct only in English in this class. So others, whenever you are asking a question, you may ask me in any language, but the answers will be in English, just to make sure that everybody understands. Okay?
Okay, thank you, sir.
So absolutely, not a problem. So let us start. We will start with okay, so let's see. Share the screen. Can you see my screen?
Yes, sir.
And is the screen moving if I move? Slides are moving?
Yes, sir.
Okay, good. Just a second. Let me see if somebody is trying to join. Yes. Noshkor. I think he's trying to join. Good. So let's go back again. Okay, here. So this is essentially your syllabus, so to speak. So we will start with the part that I will teach, that is. So we will start with structures of solids, atoms and their binding, bonds, crystal structures, unit cells, etc. Okay, but that is the syllabus. That's only the structure. What I would like to do is do it a little bit more, interestingly. So let's start with this picture. Can you see this slide? All of you?
Yes, sir.
Can you see it? Okay. So can you see what it says? It says the scale of things. Why is it that we care about the scale of things? Because at the end of the day, we are looking at modern devices which are nanometers in scale. Okay, so we will talk about scale of things. So on one side, you have the things that are natural, and on the other side, you have the things that are man-made. So like an ant is comparable to a pin. Natural, man-made. And now if you make it smaller and smaller, okay, so can you see the human hair? Can you see a picture of the cross-section of a human hair?
Yes, sir.
Yes, sir.
60 to 120 micrometers wide. So equivalent to that, if you look at the screen, you'll see something called micro electromechanical or MEMS devices. Okay, so these are very special class of semiconductor devices which are used for sensors. Okay, so what does the picture remind you of? The MEMS devices, what does the picture show? What does it look like? Yes? So can you see the picture, right? You can see the picture, micro electromechanical devices? Yes or no?
Yes, sir.
And what does the picture remind you? What does it look like? It's a picture of what?
Gears.
Gears, right? That's fine, gears. And you can see these are very, very small. They're comparable to the human hair width. Okay. So these are very, very small mechanical structures which are used to make very small motors, pumps, etc., etc. This is also very much a part of electronic devices, semiconductor devices. Okay. But they are larger than our usual semiconductor devices. They are 10 to 100 micrometers. So the dimension, we have gone from millimeters to 100 micrometer. How much is 100 micrometers in millimeters? 100 micrometer is how much in millimeters?
So 0.1.
0.1 millimeter. So if you remember, these are small structures. So these MEMS structures are used in making sensors. Okay. So how many of you have thought about this? You have a cell phone, right? Now, the cell phone, if you choose appropriately, it will allow you to see your picture or your letters in either the landscape mode or the portrait mode, right?
Yes, sir.
So how does it know which way you're holding the phone? It automatically adjusts. How does it know if you're holding the phone one way or the other? Can you try to guess? How does it know?
Sir, the gravity sensor works.
Yes, what kind of a sensor? What is it looking for actually? It is sensing what?
Sir, is it sensing the sense of gravity?
It is sensing the sense of gravity, essentially, yes. Exactly that. So essentially, if you can think of it, it's like an oscillator, like a pendulum. So the pendulum knows which way is gravity, right? Because that is the
Yes, sir.
0th point. So if you rotate it, the pendulum will change its direction accordingly. Point always pointing towards gravity. So it's a mechanical structure, but this structure, what it does is it allows you to know which way is the up and which way is down. So that is a sensor. So these class of sensors are called MEMS sensors. Why? Because they are not electrical devices, they are electromechanical devices. Okay. There is one more example for a MEMS device. You know that the cars have, for example, airbags. Yes, modern cars, they have airbags.
Yes, sir.
So what does it do? Airbag? How does it work? It expands, right? Now, how does it know there is a crash? How does the car know that there has been an accident? What do you think it senses?
The speed of the car.
No, but speed is a speedometer. How if that was the case, every time you brake, it should expand the airbag. No. Right? What does it sense? Essentially, what it senses is during an accident, the car is brought to a stop very quickly. It senses deceleration, the opposite of acceleration. Okay, it's not the speed, it's a rate of change of speed. Okay, so the sensor senses that how quickly the car is bringing itself to a stop. So that is also a sensor, which is a MEMS sensor, a micro electromechanical sensor, because deceleration, acceleration, these are mechanical things. Okay, but it measures it in a electrical fashion. So that is a MEMS device. These are also very, very important electronic devices. If any of you are looking forward to a career in devices, development of new devices and things like that, so sensors is a big area and MEMS is a very big area for your, both in the industry as well as in research, because a huge amount of sensors are being made every day by many, many companies. Okay, now let's try to make them smaller. Can you see red blood cells?
Yes,
the
sir.
equivalent size device or structure, there is called a zone plate. Can you see a zone plate? So how many of you know what a grating is? A diffraction grating? You've read about a grating?
Yes, sir.
How does it work? What does it do? It is like lines which is marked onto a metal or onto a glass very, very close to each other, and then it disperses light, right? So a zone plate is like a grating, except it is circular. Can you see that? It's like a circular
Yes,
grating.
sir.
So this acts as a lens. It focuses light, okay, using the same principle. Here also, the distance between the rings is the same or similar to, see, 35 nanometers. So these are very, very small numbers. The whole thing is similar to the red blood cell. So if you want to make it even smaller, now you go to the nanometer scale. Can you see DNA?
Yes, sir.
And what is the diameter? 2.5 nanometers. Next to the DNA, this is what we are going to focus on. Can you see atoms of silicon? That's the image of atoms of silicon. So if you look at this image, what is the first thing that comes to mind? It is a random distribution of atoms? Is the atoms placed in a random fashion or in an ordered fashion?
No, sir, it's organized. Ordered fashion.
It's an ordered structure, right? See, the atoms seem to be lined up in a perfectly ordered structure and things like that. So this is a crystal of silicon. We'll talk about crystals. On the other side, man-made things. Can you see the carbon nanotube?
Yes, sir.
And see, again, if you look at it, can you see if it is ordered or is it random? The patterns?
It is also ordered.
It's also ordered. And what is the symmetry? Is it square?
It's hexagonal.
It's hexagonal. Okay. So we are now talking about crystals and orders which are hexagonal in structure. So already we are talking about ideas that man-made structures like carbon nanotubes, these are not disordered structures. These have a very particular order. And the dimension of the carbon nanotube is 1.3 nanometers, which is similar to that of DNA. So we are making routinely man-made structures which are similar to the structures found in the natural world. That is what I'm trying to say, that electronics deals with very, 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 very small structures in a routine fashion. Okay? Most of our electronic devices, they talk about very, very small structures. Okay? That is a take-home message. Is that clear?
Yes, sir.
So we will move to the starting point. Starting point is nanomaterials must create small structures. And how many transistors are there in a chip? Tens, hundreds, thousands, millions? You know, the chip that you have, the Qualcomm chip or any other chip that you have in your computer or your phone, how many transistors do you think are there overall?
The thousands.
No, it's
millions.
millions and billions actually. Very, very large number. So basically, you have to create, must be made in millions and billions. It has to be reproducible. Everything must look identical. So in order to make electronic devices, what are the requirements? Small things and must be made in millions and billions, and they must be identical to each other. Now, if you look around you, have you seen two things which are identical to each other in the natural world? Have you ever seen two things which are really identical to each other?
No, sir.
Can you see two trees which are identical? No, right? Even within a tree, two leaves are not identical. Yes?
Yes, sir.
So we are talking about something which is very strong requirement, that we have to make very small things, very large number, and they must be identical to each other. So in order to do that, we have to take the help of nature, and that is how we start with the idea of crystals. So this is a picture of several things. There is a crystal. Which one do you think is the picture of a crystal?
Sir, the green one.
Yes. Why? Why do you think it's a crystal? What does it show? What is the property that made you think that it might be a crystal? It has what? Shiny facets. Some parts are very, very smooth, and then sharp angles. Yes?
Yes, sir.
So that is what you will need when you talk about crystals. They have shiny facets. And then you have a picture of, say, brass, aluminum, cast iron, metal, copper. So these are not crystals. They are something called polycrystalline materials. What they are, we'll talk about in a later slide. But they are not single crystals. And finally, you have glass. Can you see this glass rods? So are the glass materials crystalline, or are they something else? First point is glass solid? Do you think glass is solid or not? In order to be a crystal, first it has to be a solid. So is glass a solid material? That's the first question. Why do you say so? Because it feels solid, right? But class 8 or class 7 definition, solids have what? a fixed melting point. Yes? Class
Yes,
7
sir.
physics. Solids must have a fixed melting point. Yes?
Yes, sir.
But think about it. Do you know what happens if you heat glass? It softens. It becomes soft. It does not become a liquid immediately. It slowly loses shape. It becomes soft. And then if you keep heating it up to a higher and higher temperature, then it becomes liquid. So it does not actually have a fixed melting point. So it is like pitch, the one you put on the roads. What happens in summer?
It melts.
It starts to melt. It first gets softened, right? It doesn't really melt, but it gets softened. If you walk, you
Yes,
can
sir.
make an impression of your shoe on it. Yes. So it is neither a solid nor a liquid at that stage. So these materials are called supercooled liquids. So these are like liquids which have been cooled below their freezing point to a point where it has become very, very viscous. Viscous means that it has the flow of the liquid is very difficult, but it never really solidified to form a solid. And of course, there are no ordered structures inside a liquid, so glass is called amorphous. Amorphous means there are no structural order within the glass itself. So within here, you have a crystal, you have completely disordered structures, which are glasses, and then you have something called polycrystalline materials, which are, but as we will talk about later on, crystals are very, very small crystallites, but they are all mixed together. So it's not a large crystal. It is a material made out of many, 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 many small crystals, and therefore they are called polycrystals. Most materials we know of are polycrystalline materials. Okay. So from there, let us start having this idea. Can you see this picture now? So this is like
Yes,
an
sir.
island somewhere in Scotland or Ireland, I forgot. So what do you see? Can you see that the island is made out of nearly symmetric columnar structures? So crystals can be small, crystals can be large. Okay? You can have very, very small crystals, you can have very large crystals. So these have a certain property. The properties are flat facets, straight lines, clear angles. Okay? That is the nature of a crystal. That is what you will know looking at it from the outside. Now we are going to look at from inside. What does it do? Now comes the physics or the definition part. Let's look at the first line. What does it say? It says an ideal crystal is constructed by infinite repetition of identical structural units in space. Let's go to this picture and then we will come back to this. Can you see this picture now? This blue thing
Yes,
is
sir.
a box. Okay? It's a cube.
Yes, sir.
And I am repeating it in X, Y, and Z. So, like this, repeating, you can cover entire space. You can be a mile long and a mile wide and a mile deep. Yes? As you can,
Yes, sir.
as long as you can repeat this box in all 3 dimensions. Yes? So that is the whole idea of a
Yes.
crystal. There must be a unit which then repeats in space. So ideal crystal is constructed by an infinite repetition of identical structural units in space in all 3 dimensions. In a simple crystal, the structural unit is a single atom, copper, gold, silver, aluminum. But the structural unit may be also many atoms or molecules. Okay, we'll look at it. For silicon, you'll see it's more than one atom. The structure of all crystals can be described in terms of a lattice. Can you see the word lattice? Can you see the word lattice here
Yes,
in
sir.
the third line, in the third bullet? Okay.
Yes, sir.
So what is a lattice? Let's define. The lattice is defined by three fundamental translational vectors, A1, A2, and A3. What is a vector? What is a vector? Anything that has magnitude
Both
and
the
direction.
direction and magnitude.
Good. So you have looked at three translational vectors, A1, A2, and A3. Okay. Now, let's look at a point R. Okay, a point in space R. And then from that point R, we are viewing another point, R prime, such that R prime is equal to R plus U1 into A1 plus U2 into A2 plus U3 into A3. What is A1, A2, and A3? Three vectors. And what is U1, U2, and U3? Three arbitrary integers. Okay. Now let's go back to this picture and then we will look at it. So, in this box, okay, can you see? Hold on. Okay, can you see my pointer on the screen? Is it moving?
Yes, sir.
So let us look at this point. Can you see that point I am marking?
Yes, sir.
So now we are moving this by one vector to this point. So this vector is which vector? This translation? From here, it goes to here. Yes? Can you see that? Let us consider that vector A1. And then another vector. Can you see that? From here to
Yes,
there?
sir.
That is A2. And the third one is here. This is A3. Yes? Now, what is A1 plus A3? A1 was this? Yes? And which
Yes.
one is A3? Where do we go for A3? If I go A1 plus A3? Remember, this was A3. This was A1. This one is A2. Okay. A1 plus A3 means which way do we go?
Sir, the leftmost corner,
Here.
upper leftmost.
Right? Right? A1 plus A3 is here. What is A1 plus A3 plus A2? A1
So
plus
downwards.
A3, A2.
Yes, sir.
What is A1 plus A3 plus twice A2?
It's the lowermost left side.
This one. Yes. So what am I saying? If I multiply these vectors by unit numbers, 1, 2, 3, 4, and you add them, you come to some other point. Yes. So from here,
Yes, sir.
we have translated to this point. A1 plus A2 plus 2A3.
Yes, sir.
Okay. Now, if this was 1 mile in dimension, would you know if you are sitting here or sitting there? If this box was like inside a structure which was 1 mile in dimension, very, very large number, very, very infinitely large, would you be able to say whether you're here or you're there?
No, sir.
No, they will be identical. Yes, because they look exactly the same in all directions. So that is the point.
Yes, sir.
Looking at this, let's go back. What I'm saying is, when you come to a point R prime, where R is equal to U1 into A1 plus U2 into A2 plus U2 into A3, then the atomic arrangement looks the same in every respect. Then we can say this is a crystal lattice. Lattice, what does it consist of? 3 fundamental translational vectors, A1, A2, and A3. So the points of R prime defined by this equation 1 for all U1, U2, and A3 defines a lattice. So coming back to this point, if that was A1, A2, and A3, then together this thing defines something called a cubic lattice. Okay, it defines something which is called a cubic lattice, where all of these points are placed in a structure which has a cubic symmetry. Any questions regarding this? So lattice is something given by 3 fundamental translational vectors and numbers n1, n2, n3, n4, which together define the entire geometry. And the symmetry, of course, is given by the symmetry of the A1, A2, and A3. So this entire geometrical structure is called lattice. Any questions regarding this? Anybody?
No, sir, it's clear.
Okay. So geometry is called lattice. What you place at each point is called basis. Okay. You can have one atom. So the crystal structure is formed when a basis of atoms is attached identically to every lattice point. So here, for example, we had one atom per lattice point. We can have 2. We can have a cluster of atoms. We can have molecules. The same crystalline symmetry remains the same, cubic, but the crystal will change because whatever you put in is called the basis. So basis plus lattice together, they form the crystal. Okay. So what is the basis? Basis is whatever you are putting in. And what is the lattice? Lattice is the geometrical shape. In terms of something that you can really understand, okay, how many of you have been to Rajarhat? How many of you have been to Rajarhat or Newtown? Okay, so it's like an empty space with a lot of plots, yes? So the plots are the lattice points. The houses, whatever you build, are the basis. Okay, so because you could build a red house, you could build a white house, you can build a green house, does not matter. So the plot, the geometrical distribution is the lattice. Okay?
Okay, sir.
Now, this A, B, and C, these 3 crystal, they are called vectors, right? They are given by what? Magnitude and what does vectors have?
Direction.
And direction. So here comes the fun part, that they are defined by the magnitude and the direction. So if this was your origin, A, B, and C, what are they defined by? The length of A, B, and C and the angles between A and B, B and C, and C and A. These angles are called alpha, beta, and gamma. Okay? So these are the 6 important parameters, A, B, and C, and the angles between them, alpha, beta, and gamma. Depending on this angle, you have unit cells. This unit cell is cubic because A is equal to B is equal to C. And what are the angles in degrees?
90.
90 degrees. Okay, so this is cubic. But of course, it may not be cubic, it may be something else. So, can you see this? So these
Yes,
are
sir.
the various types of crystal lattices. The first one is triclinic. And if you look at the restriction, what are the restrictions? See, it has no restriction. A1 is not equal to A2, is not equal to A3, and alpha is not equal to beta, not equal to gamma. So that is called a triclinic unit cell. It can be in a random fashion. And then you have monoclinic. So what is the difference? Can you look at the table and tell me? How is the monoclinic crystal? What does it say? Can you read it? A2A3. So basically, but not equal to beta. So basically what is happening is, if you look at it in a bigger picture, okay, so B is like this, but one of them is 90, the other angle may or may not be 90, okay, and so forth. You have orthorhombic, you have tetragonal, you have cubic, trigonal, and finally hexagonal. These are the various symmetries of the crystal structure. I will assign this as a homework so that you can draw it and put the table there, so you will know what are the important crystal lattices. Not all of them are cubic. And so I have a picture. Can you see a picture here on the top and the bottom? They look like crystals, right? Natural crystals. So the top picture, what does it look like? What is the symmetry? It's not perfect, but can you see it has a cubic nature?
Yes, sir. Cubic.
It's cubic. The bottom one, can you see it's also a crystal, but it doesn't look like cubic?
Yes, sir.
Okay, so each crystal has its own symmetry, and depending on the symmetry, you can say they are monoclinic, orthorhombic, etc., etc. Okay, now within the cubic, now there are three types of cubic: simple cubic, face-centered cubic, and body-centered cubic. This is a simple cubic. So what is the difference between a simple cubic and a body-centered cubic? This one, these two? In the simple cubic, what do you have? Atoms at where?
Corners.
Corners. And in the body-centered cubic, there is an additional atom.
Corners.
Where is it?
Yes, sir. At
In the
this
middle.
body center.
Right, the body center.
Yes.
In the face-centered, how does it work? It has corners as well as where?
In face centers.
In the faces. Now, given by this, can you tell me how many atoms are there in this box?
Eight.
No, not 8. Why?
1.
And why 1?
Oh, yes, sir.
Because
1/8 of
1/8.
contribution. They're sharing 1/8 of the contribution.
Okay. And how about this?
2.
2. How about this?
4, I guess.
4. Why 4?
Because the face center atoms are contributing half and the corners are contributing 1/8.
Okay. And how many
There
faces
are
are
total
there?
6 faces.
Okay.
There are total 6 faces, so 6 into half, 3 plus 1.
Good. So these are the different kinds of cubic systems: simple cubic, face-centered cubic, and body-centered cubic. Now we will come to the diamond lattice. Now it looks complicated, yes? Silicon has the same structure, so we can also call it a silicon lattice. Now, everybody can see this picture, right? This one? So
Yes, sir.
if you notice, this is a cubic. Okay, first point, is it cubic? Yes, it is cubic. You can see a cubes. But then see what is happening. 1, 2, 3, 4 on the corner. And this one is at the face center. 1, 2, 3, 4 at the corner. This is the face centered. So this is actually a face centered cubic. But there is an additional atoms which are there, which are not there in the normal face-centered cubic atom. So what is the additional atom? It's here. This atom does not belong in a normal FCC, yes?
Yes, sir.
So silicon is an FCC structure, but there are 2 atoms per base. That is point. One is at where it's supposed to be. The other one is 1/4 the body diagonal. So this is the body diagonal. So from here, if you walk along the body diagonal and go 1/4 the distance, you will find this atom. So this is an additional atom placed within the unit cell, 1/4 the body diagonal away. This is a FCC, the center of the face atom. Yes? Can you see that? It's the center of that face.
Yes, sir.
Now, if I walk along the body diagonal and go 1/4 the distance, I'll find this point. So this is an additional point. So can you see this is an FCC structure? This is the face center of the bottom face. Right? The center
Yes,
of the
sir.
bottom face. But if I go 1/4 the body diagonal, I'll find this plane. So similarly, we have a whole lot of these structures. Like this is the face center. You go 1/4 the body diagonal, you find this. So there are 4 atoms inside which are additionally placed along with the face-centered structures. So that is the crystal structure of silicon, which is the most important semiconductor. So you need to know what the crystal structure looks like. So what does it look like? It's a face-centered structures, but there are additional atoms. What are the additional atoms? They are 1/4 the distance of the body diagonal. So how many atoms were there in the FCC anyway? We just said the FCC has how many atoms in the unit cell?
4.
4. Now we have 4 more which are inside. Can you see that?
Yes.
And these 4 more are along the body diagonal 1/4 the distance. So that is the unit cell of the silicon. Now this top picture, it looks at the same structure looking from the top. And these numbers indicate height from the base. So 0 indicates atoms which are at the base. So can you see how many zeros are there?
5.
Right. Where are they?
Sir, at the 4 corners and at
At
the
the center.
center.
Yes. The 4 corners and at the center. And now we are going up vertically. We go to the 1/4 distance. Can you see how many atoms are there extra? 1/4 and 1/4. 2 more.
Yes, sir.
Okay. And then you keep going up. Go to half. Where how many atoms are there in the half position?
4.
And where are they? They are the
The face centers.
There's the face centers. Yes. And then you keep going up. At the 3/4 location, you have 2 more. And they are connected 1/4 the body diagonal, as I said. And then you go to the top, you get again
Yes.
5, which are the 5 on the top. So this defines the silicon lattice. Okay. This is also the same as the diamond lattice. They have similar lattice structures. Of course, lattice talks about only geometry, right? So you can say this has similar geometries. Okay. Any questions regarding
Yes.
the silicon lattice? If not, we will move to the next slide. Have you been introduced to Miller indices before?
No, sir.
Okay. So this is a way to define atomic planes. So how do you do that? You have the X, Y, and Z axis. right?
Yes, sir.
Now, first point is you find, see, this is the plane. Can you see where the, can you see that? Where does the plane intersect the z x-axis? Where does the plane intersect the x-axis? At which point? See, what does it say here? What is this point?
3.
3. Okay. Where does it intersect the
Yes.
y-axis?
At 2.
2b, right? And where does it intersect the z-axis? 2c.
2.
If the unit A, B, and C, so intersects are 3a, 2b, and 3c.
2.
3a, 2b, and 2c. So the way to do this, you take the reciprocal of these numbers. 1/3. What is the reciprocal of this number? Half. What is the reciprocal of 2?
Half.
Half
Half.
again. And then you simplify it. How do you simplify? You multiply throughout by 6. Then you get the numbers 2, 3, 3. Yes? If A is
Yes,
equal
sir.
to B is equal to C, these are 2, 3, 3. Yes? And then
Yes,
what
sir.
do you have? You have this plane which is called the 2, 3, 3 plane. These are numbers called Miller indices which indicate which plane this is. Okay, now let's go to this picture. This red plane. Where does this plane intersect the x-axis? Let us say it intersects at 1. Now, this red plane, where does it intersect the y-axis?
One.
No,
So did
it intersects the
infinity.
x-axis at infinity. And the z-axis?
So also infinity.
Infinity.
Okay, so if you take the inverse, what will happen?
So 1, 0, 0.
1 by 1.
1, 0, 0.
So this plane is called the 1, 0, 0 plane. Now take this plane. Where does it cut the x-axis? Let
1.
us say 1. Where does it cut the y-axis?
1.
And where does it cut the z-axis?
Infinity.
Infinity. So this plane is
1, 1, 0.
what is 1, 1, 0. Okay. And this is 1, 1, 1 because it cuts
Yes,
the
sir.
plane at 1, 1, and 1. So these are the way to define Miller indices. Now let's look at this. This cuts the plane at half. X at half. Y at infinity, Z at infinity. What will be the Miller indices?
2, 0, 0.
2, 0, 0.
2, 0, 0.
Okay. And now
Yes, sir.
let's look at this. It cuts it at minus x, minus 1. So this minus is defined like a bar on top of the 1. It is called 1 bar 0, 0. Okay. It just means this is going in the negative x direction. So this is the plane. Okay. So these are the ways to define Miller indices. It's another picture. Does not matter. The same story. So, any questions regarding Miller indices? It's simply a notation for
No,
you
sir,
to
it's clear.
define which plane is which. Okay. Now we will talk about another component called packing density. Now, what is packing density? It is simply a way to say how much material is in the unit cell, how much is covered by the atoms, and how much is covered by space? What is the ratio? Okay. So in order to do that, we are making certain assumptions. We assume atoms are like hard spheres. Of course, atoms are not like hard spheres, but that's an assumption. And they touch each other along closed packed directions. We'll look at this picture. So this is a unit cell of a cubic structure, and we have cut it. Can you see that? So can you see the 1/8 of the atom?
Yes, sir.
And how are they touching? They are touching along the closed packed direction, which is the A. So if the distance is A between the two atoms, how much is the radius?
A by
A by 2.
Right? R is equal to A by 2, because they are touching along this direction.
Yes, sir.
Now, so how many atoms are there? 1 in a simple cubic. What is the volume of the atom? 4/3 pi.
Pi r cube.
R is 0.5 A cubed. So this is the volume of the atom. And the volume of the cell is how much?
A cube.
Okay. So what is the ratio? This by this, it comes to be, can you see this number? So that is called the
0.5.
atomic packing fraction for a simple cubic lattice structure. Any questions regarding this?
No, sir.
Now let us go to a BCC structure, body-centered cubic. So there, the closed pack direction is the body center, body diagonal. Yes. So can you see this is one, this is the other, and this is the third, the one at the body center. So how many radiuses are there from here to there?
4.
4. And what is this length if this was A?
So root 3A.
Yes. Do you know why? Because from here to here it is root 2A, and then the body diagonal is root 3A. Okay. And so 4R is equal to root 3A. Now, how many atoms are there in the BCC?
2.
2. What is the volume? 4/3 pi R is root 3A by 4 whole cubed. Yes, by
Yes,
A
sir.
cubed. So that is the packing density of the BCC. What I will do is I will give you the homework assignment in which you will calculate the packing density of the BCC and the FCC. Okay, so it's already 1 hour, huh? Okay, so we'll stop now, and I will give you the homework. So when is the next class for us?
Sir, tomorrow.
Tomorrow at what time? Same time?
4:30. Same time.
4:30. So we will see you again tomorrow. Okay. Thank you so much.
Okay, sir. Thank you. Thank you, sir.
Thank you, sir.
Thank you, sir.